Well, hello and welcome, everybody, to another episode of our post-based seminar series. As always, here are all of the links associated with the series. Please feel free to share them as widely as possible. Um, as always, if you have questions during the talk, just put them in the chat or the Q&A function, and Matthias and I will interrupt Pascal and ask them. And otherwise, we'll have some time at the end. We're now just past the halfway point of our PAC-Bayes chapter. And today we've got Pascal Germain, who's been working for a while now on the more machine learning side of PAC-Bayes, and who's going to talk to us a bit about that today, and in particular about some really interesting work I've seen a bit about on this kind of hybrid theory between PAC-Bayes and sample compression theory. So I'm super excited. So over to you, Pascal.
Thank you for the invitation. So today I will present you work that I did recently on PAC-Bayes and simple compressed hypernetworks. I will talk more about the PAC-Bayes side because it's a PAC-Bayes seminar, but I will talk a bit about how we can use the simple compress, which is another statistical learning theory, uh, to mix it with PAC-Bayes. So I like to begin my talk with this graph that I update just before each talk. I guess I don't have to convince you that PAC-Bayes is nice, but it's interesting to see here is the result the number of results that we obtain on Google Scholar when we search for the PAC-Bayes or the PAC-Bayesian keywords across the years. So we can see that in 2017, 2018, there was a shift where PAC-Bayes becomes increasingly popular. And this is thanks to Dan Roy and Carolina Zugate that published a paper about using PAC-Bayes to get self-certified neural network. And we'll talk a bit about this work later. Um, Okay, so the subtitle of my talk today could have been the mechanization of PAC-Bayes. So it's always fun also to begin a talk with a quote. In here, I quote a classical textbook in computer science, and in fact, I'm much interested into the title of chapter one, which is that the computer science is the mechanization of abstraction. So what I will focus on today is the use of PAC-Bayes theory to design a new machine learning algorithm. Um, I will present a way that we develop, which is, I think, pretty original, uh, in which we craft neural network architectures inspired from learning theory principles. So, like I said, I will focus on PAC-Bayes, but I like to think that this idea, this way of thinking about designing neural network architectures could be applied to other learning theory. And I also think that what I will present is a step towards obtaining guarantees for what we call nowadays large models or large language model, foundation models, or this kind of things. And I said that this is a perfectible step because I will not, in my talk, obtain guarantees for this kind of monstrous models, but I think the same ideas could extend to yeah, to this kind of models. So I'm not the first talk about PAC-Bayes, so I will not go into all the details. Other than that, before me quite well. Here I just define my basic notation. So I will start to work with in the classical supervised learning prediction setting. So I will call each observation a learning example. So a pair XY that I denote sometimes Z, which is belongs to a certain input-output space. And I will assume that each example, each Z is drawn according to distribution D. So the learning sample would be only a set of n observations drawn according to this generating distribution. And I will study hypothesis, so a function that map x into a y. Learning algorithm will be denoted A, take learning sample S and output hypothesis H, and we will study a loss function that return a loss value. I will denote the empirical loss L at, and the generalization loss just L subscript D, because it's the generalization loss on the distribution D. So here is perhaps the most classical PAC-Bayesian theorem, which is uh, valid for a prior distribution P over the set of hypothesis H. And the theorem say that with high probability, so greater than 1 minus delta over the draw of the training set, the expectation of the generalization loss, which is the expectation according to a posterior distribution Q that we will learn, is upper bounded by the empirical loss on the training set and a certain complexity term. The complexity term in the most classical PAC-Bayes bounds rely on the Kullback-Leibler divergence between the posterior Q and the prior P. And there's many assets to this kind of results. And I repeat here that what I will focus on today, it's the use of PAC-Bayesian theorem to derive new learning algorithm. And one aspect that I want to emphasize is that particularity of this kind of PAC-Bayesian bounds is that the bound is valid for all posterior Q. So contrary to classical Bayes results, say, the bound is not only valid for the posterior that minimizes this term. So it's quite convenient when we are doing gradient descent to optimize a neural network, say, because as you know, there's often many local minima, and people do early stepping to choose a solution. But we can compute a bound, and the PAC-Bayes is known to allow to derive a numerical tight bounds for any solution, even if it's not the optimal one. So I presented you the classical bounds due to David McAllister. Another classical PAC-Bayes theorem is this one, which is the tighter bound that we can obtain for the 0-1 loss. So it's a little bit more difficult to parse. But it says that the function here, so that I call the small KL, is between the empirical loss and the generalization loss is less than the complexity term that we have here. And this small KL function is the Kullback-Leibler divergence between two Bernoulli distribution, which I wrote here. From an algorithm design perspective, even if it might be more difficult to understand this result, the KL bound is allowed to derive easily learning algorithm based on gradient descent because it is in fact differentiable. So here I put a reference. I think this paper is the first one that explicitly derived the derivative of the inverse of the KL. And here there's a PyTorch implementation that one can use to optimize this kind of Bayesian bounds in PyTorch. Um, one other interesting fact is that we can also minimize the bound by minimizing this term. So adding another parameter which we can also optimize on. And in fact, the minimum value according to C of this linear formula will give the same answer than the inverse of the KL. So it's also quite convenient when we want to implement PAC-Bayesian optimization algorithm. So here I will discuss a bit the classical way of using the PAC-Bayesian bounds to derive learning algorithm, uh, which is just to take, say, a neural network architecture and consider the P and Q distribution, so the prior and the posterior distribution, as distribution over the parameters of the neural network. So it can be any kind of predictor which is defined by a fixed number of real value parameters. And what is usually done in a lot of work, including the work of J. Gate and Roy that I referred to at the beginning, is to only consider a normal, so Gaussian distributions over the weight of the neural networks. So W here, WP is either the random initialization of the weights of the neural network, or we can learn it on a dataset that we discard for the second phase of the training, so a kind of pre-training. So we consider a Gaussian distribution over each individual parameters, and we can learn also a standard deviation term. And when we are doing gradient descent, in fact, we are also optimizing the weight W and possibly the standard deviation term sigma here. And what people usually does is to do at each gradient descent step, uh, randomly draw weight according to this normal distribution and perform a gradient step over the weight that they draw. Again, from an algorithm design perspective, this choice of prior and posterior is very convenient because the cutback library distribution between the posterior and the prior that we have in the complexity term of the bound is only the squared Euclidean distance between the learned weights and the weights of the prior. Um, so this method is known to allow to learn weights of a neural network, give quite good result. And what is interesting that we also observe that we obtain type guarantees. What I present here is result that is available in the work of Perez, Ortiz, and al. In 2021. It's a GMLR paper. It's heavily based on the work of Zuget and Roy, but their algorithmic choices made the implementation much more easy to understand, in my opinion. And just for an example, when they learn a neural network with convolutional layer on MNIST, the full MNIST, they obtain a risk certificate of 1.55%. With probability greater than 95%. So it's quite a tight uh, risk bound, and I don't know a lot of statistical learning theory that can achieve this kind of numerical results. And like I said, it's quite easy to train, so I put the link here to their implementation. Uh, but in fact, so this is really good. But this is not adapted to nowadays big, large models that have a huge number of parameters. And the reason is quite simple. In fact, and Pierre Aki, in his previous presentation in this series of seminar, uh, show well that when we have an increasing number of dimension and we are using this kind of prior and posterior, the KL term tend to increase very much. So when we have a huge number of parameters, this bound can degrade. So what I will present now is a work that I did with my students called Generalization Bounds via Meta-Learned Model Representations, PAC-Bayesian Simple Compression Hypernetworks. So it appeared in last ICML. And I enter now in the much more machine learning part of my presentation because I will present quite um, not complicated, but a big neural network architecture, uh, which I base my result on. So here I want to present you the idea. So I said that one problem with when we use Gaussian prior and posterior distribution over all the parameters is that the KL can blow up. What we will do is to put us in a meta learning framework where we assume that we have access to a lot of data and more particularly here we will assume that we have access to several data sets that are all belonging to the same family of tasks. And we will learn what we call a hypernetwork on these several tasks. So the hypernetwork will take as an input a data set. So here I call this data set the support set. So I, for the moment, just consider it as a regular training data set that we will give this data set to a neural network component, which we call the encoder. Later on, I will call it the compressor when I will talk a bit about simple compressed theory, but now let's consider it as an encoder. And this encoder will give a small latent representation of the dataset. So what I will explain later is that this latent representation can change depending on the kind of learning theory that we want to use to derive risk certificates. But now we can consider it as only say a hidden layer of a neural network, so a vector of real parameters. And uh, this vector of real parameters, so this representation, will be given as input to a decoder, which I will call in the simple compression framework later the reconstructor also, but now we can see it as a decoder. And the aim of the decoder is to output a predictor. So in more in details, it will output parameters of another small neural network. So it might appear a bit complicated for now. The idea here is that the latent representation act as an explicit bottleneck, and we will compute the bound on only these parameters. So this is the first high-level overview. I will go into a bit more details in the next few slides. Uh, Now I define the supplementary notation that I need to express my meta-learning framework. So now I have a collection of dataset. So each S1 to Sm is a dataset belonging to a task in particular. And I have a data distribution Di, which belongs to each in fact, according to which each data distribution will be drawn. What I call my meta-learning algorithm is a learning algorithm that will take as input these collection of dataset and will output parameters. Now, here my parameters are a pair. Phi is the parameters of the encoder network part of my architectures. So it's the parameter that will define this part of the neural network, and it will the encoder is denoted script E here. So the role of the encoder will be to receive dataset S and output a vector that I call mu here. And so I go back to my meta-learning algorithm. It also outputs another set of parameters that I call phi here, psi, sorry. And this psi are the parameters of the decoder. So the the role of the decoder will be to take as input the vector mu and output theta, and theta are the parameters of what I call the final predictor or the downstream predictor. So H is parameterized according to theta, and this is say a regular predictor which take X as input and outputs Y. So the thing here is that to obtain valid PAC-Bayesian bounds, the encoder and the decoder must not be learned on the same dataset that we construct the downstream predictor H theta here. So it's why we are putting ourselves in this meta-learning framework, when we will learn the encoder and the decoder part on a relative task. And after that we have obtained an encoder and a decoder, we will use this meta-learning algorithm to learn on a new dataset S. And once we are doing this, this is convenient because we will use the the PAC-Bayesian bounds that we already know to obtain a valid risk certificate using only the latent representation of the predictor that I call new here. So here it's the picture that explain the what I call the PAC-Bayes hypernetwork. So it's very similar to the picture I presented you a few slides back, but I detail what I call what is the latent representation of the dataset for the case of the PAC-Bayes bound. So the encoder will output a vector, which is called the message here. So the message is a terminology that comes from the sample compressed theory that I will present soon. Since in PAC-Bayes we are working in expectation, in fact, we will add to the message before giving into the decoder a small perturbation. So the drawn of a vector according to a normal distribution. And will be given to the decoder, which will output the parameters of the downstream predictor. So to be a bit more precise, each dataset of the meta training dataset is split into two disjoint set, what people in the meta learning literature call the support set and the query set. So the support set here will be the set given to the encoder for learning, and the query set will not be used directly in the encoder, but will be used to compute the loss on the parameters of the predictor that are given by the decoder. So here is the objective that we optimize by regular gradient descent. So we have the mean, the empirical average of the loss on the query sets. And here we have the parameters theta I. So I is the index of the dataset Si, which is given by the decoder, and the decoder is fed with the mu I, which is the output of the encoder, and the noise epsilon, which is drawn according this normal distribution. So what we do when we optimize that is to optimize on the parameter phi and psi. And once we have learned this neural network, we can learn on a new data set, so a new task sample, which I call X prime here. So what I do in that situation when I want to use the learn hypernetwork is only to feed the new dataset S prime to the encoder and obtain at the end the parameters theta of my downstream predictor. But what now is convenient with my PAC-Bayesian bounds is that I can directly compute a risk certificate on the predictor that my hypernetwork just outputted. So this is the same PAC-Bayesian bound with the small scale function that I presented to you. Here I consider as a prior normal distribution over the zero vector, which correspond to the non-informative prior over my latent representation. And the posterior is a normal distribution centered on the vector mu, so over the latent representation that I obtain given a dataset S prime. So to show you that it does at least partly what we want. Here I present you result that we obtain on a toy experiment. So it's based on the very common two moons dataset, but we want to use it in a meta learning scenario. So what we did is to generate points according to this two moons dataset, and each different learning task is created by applying a random transformation on the classical two moons. So we rotated the moons, we performed some scaling and some translation, and the old architecture here is learned on several transformation of this two moons dataset. So what I want to show you here is that it learns something relevant. Uh, Here, because it's a toy example, uh, what we uh, what we use as a latent space is a vector in two dimension. So the we can say that the decoder take as input a vector of two dimension, mu1, mu2. And this is convenient because we can actually see what kind of decision boundary is generated by the decoder by varying the values of mu1 and mu2. So here on the left plot, what we did is to fix mu1 to a certain value and to play with the value of mu2. So we can see here different decision boundaries. So in fact, when we change the value of mu2, the boundary is rotated. And similarly, on the right figure here, we fix the value of mu2 and we play with the value of mu1, and we can see here that the decision boundary is stretching. So this all architectures allow really find a simplified representation here only in two dimension of all the parameters that are required by the downstream predictor. And so after that, I present you results on more realistic dataset, which is based on the famous MNIST dataset. So here, in fact, I will present you results comparing what we obtained to other work that appear in the 10 last years, say, on PAC-based meta learning. So here it's the benchmark that people that does PAC-based meta learning use a lot. So the different tasks are obtained by taking the original MNIST and randomly permutating a certain number of pixels in the images of MNIST. Uh, so we have results for different for 100 pixel swap, 200 pixel swaps, and 300 pixel swaps. So here I did a selection of the different work that use this dataset, and the line of our PAC-Bayes hypernetwork is the result that we obtain. And in fact, the result that we obtain for this um, are not as good as we want. In fact, we can see that whoops, sorry, uh, I need to go back. Uh, we can see, um, so we can see that uh, we are not the best in either scenario. But uh, what we you should know is that the three first methods are methods that learn hyper prior on the parameters of the downstream predictor. And once this upper prior is learned and the algorithm see another data set, they fine tune, say the weights. So they learn in a manner which is quite standard, the weights of the neural network by gradient descent. The hypernetwork is just there to put the start the neural network in a good position. And a lot of good results are obtained by this very recent work of Zacharina. Um, and in fact, their method is to put an hyperparameter on different kind of learning algorithm or neural network architectures, and they also learn the final predictor in a standard way. So we are not obtaining the best result yet, but uh, we obtain say good enough results with a strategy that is really different than what people normally did. And what I call the opaque encoder here is the neural network that we obtain with the same kind of strategy of that we use in the our PAC-Bayes hypernetwork. But in that case, I have a message of say size 0. So in that case, the decoder is always outputting the same neural network weights for all tasks. And we can see, in fact, that this task of pixel swapping is not very difficult because outputting the same neural network for each task gives not the best, but quite reasonable results. So to try our methodology on a more complicated scenario, we create another meta learning task uh, by considering that each task is a pair of digits of the MNIST dataset. And in fact, we did the same thing using the CFAR images. And we run the algorithms of the other methods, which was not done before. And we see here that our results compare quite well to the others. Um, and in that case, in fact, the parameters of the downstream predictor must be much more different for each particular task. So on MNIST, we obtain a test server that is um, about half of the best result, and we obtain the best bound also. On CFAR, it's not the best, but it's quite competitive. Um, okay. Can I ask Jan how much time I have left?
Well, 20 minutes total
Okay,
in principle,
okay,
but
okay, that's fine. So I will talk about simple complex theory. I may skip the proof. So Here I put a lot of references just to say that the simple compressed theory is uh, was initiated, say, for 40 years ago. But in the machine learning community, it was active, to my knowledge, around uh, uh, more in the last 20 years. And I put here two lines of research on the simple compressed theory. There's other, but it's the two lines I know more. The first one is the one around an algorithm that is called the set covering machine that was proposed by Mario Marchand and John Chatelain in 2002. And the other one is much more recent. It began in 2023 by these authors, so Pakanian, Campi, and Garati, which propose an algorithm that allows to obtain tight bounds using neural network. And I started to get interested recently by this line of work, and we publish a paper on in AI Stat around this if you are interested. So here, the what we call the simple compressed theory is a way to obtain generalization bounds using a quite peculiar kind of predictor. So it's a predictor that we'll call compressed predictor that I denote H mu vector I here, which is a data-dependent predictor that we can encode by two quantity. The first one is what we call the compression set, which is a subset of the training set. So here, the vector I is a subset of the indices of the training observation. So if I have n training samples in my training set, um, I could be a vector containing indexes from 1 to n. And my compressed predictor also rely on a message that we can see as a string that contains additional information. Usually in the classical PAC-Bayes theory, the message is discrete and is chosen among a predefined set of messages. Here, I will consider that this set of messages is the same for each possible compression set indices, but we can extend this theory. And the most important things to know about the simple compress framework, if you want to understand what is coming, is that in fact um, a predictor is called a compressed predictor if there exists a reconstruction function that takes as input the simple compressed set, so a subset of the training example, and a complementary message mu, and output the same predictor that we can learn on the full dataset S. So the most classical example of simple compressed algorithm is the famous support vector machine. So the support vector machine can be seen as a simple compressed algorithm because if we learn an SVM on a dataset S, and we after that we select only the samples that are the support vector, we can feed the SVM with exactly the same uh, we can feed the SVM with the compression set, so the support vector, and we will recover the exact same decision boundary. Um, and here the SVM doesn't need a message. Um, so I will skip this part. So this is a simple compress bound. What we did in my group. one thing that we did around simple compass theory is to extend the bound to real value losses, because the classical bound was only valid for the 0, 1 loss. Uh, so I will, yes, I will skip this part. So the proof, and in fact, I want to present you another instantiation of my the kind of hyper network we play with, but this time's not for the PAC-Bayes theory, but for the sample compressed theory. And here, the latent space, instead of being a vector of real value as we did in PAC-Bayes, the latent space will be in fact, it will be a vector of 0 and 1 of the same size as the support set that we feed to the encoder. And this vector of 0 and 1 will serve as indication for selecting the example of the compression set. So here in this figure, we can see that we provide the encoder with a support set of 4 images observation, and the encoder select the first 2 to feed to the decoder. And the decoder as previously will output a vector of hyperparameter for the downstream predictor. So here I go back to my toy experiments with the various 2 moons, and here we ask to our Hypernetwork, when we train it on different moons with different rotation and scaling and translation, to select only 3 training example to feed to the decoder. So the stars here on the figure correspond to the points that our neural network select. So it's really training example, and with these only 3 points, the decoder can reconstruct the decision boundary. And after that, in the paper at ICML that I'm that contains all the details of what I'm presenting you today, we present a new PAC-Bayesian result that is in fact a mix between a simple compressed bound and a PAC-Bayesian bounds. So here it's a simple compressed bound because we use a compression set. So the bound is valid for each vector I, which are indices of selected sample on the training set. So the cardinality of I here correspond to the numbers of data point we select for the compression set. And we also consider messages, but instead of using discrete messages as it's classical in the simple compressed theory, we use a distribution, a posterior distribution over the messages. So here is the PAC-Bayesian part of this result. In fact, we apply a classical PAC-Bayesian proof to obtain an expectation on the messages here. And of course, we have also a prior over the messages, and it's why this bound depends on the famous Kubat-Labler divergence between the posterior and the prior. So based on this new theoretical result, we also try to implement another variant of our hypernetwork, which we call the PAC-Bayes simple compressed hypernetwork, which is a bit bigger architectures. Now the support set is given separately to 2 neural network component, where the first part that we call the sample compressor, which select examples from the support set, and the second one that we call the message encoder, which output vector value, so latent representation, which is of the same kind of the one that we obtain in the PAC-based hypernetwork. And these two information are given to the decoder that we can call the reconstructor here to output the hyperparameter. Um, and in the paper, we have a detailed result on the different benchmark that we use. Here, I only present you this two figure with which show the first the test error that we obtain on the MNIST binary tasks, where each task is to predict one of two MNIST digit. Uh, and we see the behavior when we vary the compression set size, so the number of sample that the first part of the neural network, the sample compressor, is selecting, and on the other axis, the message size, so the size of the latent representation vector. And roughly, we can see that the 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 tester is getting better if the two quantities are higher. Uh, and on the right figure here, we have the bound value that we obtain when we compute the risk certificate given by are bound. What is a little bit disappointing here is that the bound is better when the message size is zero, but and so the bound preferred to have a large compression set size, which does not correspond exactly to what we obtain on the test error. So it's the result that we have for now and the result that we publish, but we didn't give up on improving these results. So to complete, there's a lot of things that we can think to do using this kind of way to think to learning algorithms, but on the short term, thing that we plan to investigate is to dynamically select the message and the compression set size during the learning phase, because now it's parameters, hyperparameters of our learning algorithms. And we also think that this kind of approach is promising to fine-tune, to adapt bigger models like large language models, where we have a model that is learned already on a huge amount of data, and we just want to adjust a bit the parameters. So thank you, and I also want to thanks my collaborator. So Benjamin Leblanc, which is the main author of the work that I present today, Mathieu Besnet and Nathalie Damon that helped a lot, that helped us a lot during the writing in the experiments, and Alexandre Drouin, which is another researcher in industry. So thank you. I can now take questions if you have.
Thank you very much, Pascal. I have one again to be slightly selfish right at the beginning.
Go
Um,
ahead.
so the kind of when you were talking about what that latent space, how it's represented, something that came to mind was whether there is a connection between changing the form of the latent space with something around kind of quantized neural networks, where we're suddenly restricting the size of the parameter space from the reals down to two-bit representations of numbers, or and whether doing that is somehow a special case of what you've done, and whether it is this reduction
Uh,
in the parameter space which allows for better bounds.
I would say that there is a connection because, of course, when you are quantizing parameters, you reduce the space of possible predictors. But I think at the same time, it's a quite different strategy because um, uh, here we are really compressing the parameters into a latent vector and possibly like selecting relevant samples. But one way, I think I didn't mention it that way, but one way I like to think about this is that there is the space of hyperparameters of the downstream predictor, but there exists say a manifold, so a small subspace in that whole space where the relevance parameters lie. And I think we can see this latent representation as capturing this subspace of parameters. I don't know if it's answer your questions.
No, I think it does. I guess my where I was kind of going with it was more whether you think that there could be some way of getting tighter bounds by considering these kind of quantized spaces, but or whether that is another
Yeah,
direction to go to.
uh, we could. In fact, I did not. We did a lot of things in that paper, and but there's a lot remaining also. But one thing that I didn't talk about that is also connected to your comment is to enforce the message to be a binary vector.
Hmm.
So it helps also to get a bit better bound. And of course, we can mix all these ideas together.
Yeah, brilliant. Thank you very much. Does anybody else have any questions?
I can have one. Thanks for the great talk, Pascal. You said a couple of times that you think this like possible to extend it to more like complex models, that's like LLM, stuff like that. Like the next step will be tackle these huge models. What do you think are the main challenges there? Like, I guess one is like is the type of losses that you can consider, but then it's kind of like to me, oh, I kind of don't see how to extend it to more complicated models like that. See, I'd like to see your opinion there.
Okay, so in fact the idea that we have, I don't know if you know about there's a thing that is quite popular when fine-tuning a large language model. It's called LoRa adapter. So low ranks, it's LoRa stands for low ranks adapter. So it's basically people learn a small transformation matrix that apply to some final part of this big models. So this in practice help a lot intuitively because it reduces the space that we have to optimize. So the idea that we have here is to output this low rank this matrix with the um, with our hypernetwork architectures. Uh, but we are we are quite new to this kind of large language models word. So now, I'm trying to bring my tools to this era. We did really preliminary experiments, and right now we did not succeed to obtain good results. And but at this point, I I cannot tell why, but it's really very preliminary. Uh, I didn't give up to. Maybe there's some kind of some change that we need to do in the neural network architectures. Right now, we use quite standard multi-layer perceptron. And perhaps I should have said also, it's not your question, but people might be intrigued about uh, what we use. There's a kind of trick calling the deep set that we use to be permutation invariant to the order of the sample when we give a data set as input to this component. But we did that and it works. It works quite well for the, say, the small scale task that we were handling. I guess it might be not enough sophisticated for large language models.
Yeah, also, for the PAC-Bayes part, have you tried to drop the encoder and optimize the latent vector directly to
Uh,
minimize the bound?
the answer is no, but it's a really good idea. I thought about it and we plan to experiment it. There was just a vast landscape of things to try, and we succeed to make this work. But this would be natural, in fact, to optimize directly the PAC-Bayes bound by optimize over the latent representation. So if you want to try it, everybody can try it on their side.
Fantastic. I think that's us pretty much at time. So if anybody has any remaining questions, maybe email us or Pascal
Yeah,
directly.
I will be happy to
And
receive questions by email if you have.
perfect. And otherwise, thank you very much, everyone, for coming. Thank you very much, Pascal, once more for your talk. And we'll see everyone next time.
Thank you.
Thank you.